Hi, class. I hope everyone is having a marvelous time and that you have enjoyed part one of today's lab. So that's kind of the key thing is that we're doing like circuits part two today. Um, and before you watch what's in the rest of this video, it really would be very helpful for you to have already played with the stuff in part one, where you get to do a little bit of experimentation, test out the different parts and components to see how everything's working the way that it does. Plus, some of the things I'm going to show you in here today are kind of spoilers for some of the tasks you're trying to accomplish in part one of today's lab. So really, if you're looking for that full learning experience, you need to have uh, done some experimentation in part one. But before you can do part two of today's lab, you'll need the content that I'm going to deliver here. Okay, so um, in today's lab, you had a few tasks. You can use one battery, three bulbs. That's a bulb, right? Three bulbs and as much wire as you wanted. Okay, and you had to light each of the three bulbs and have them have the exact same amount of brightness. And then you had to do that again a second time, but the brightness level would be different. Either your first trial's brightnesses would be really dim, and if that was the case, then in the second setup they would be very bright. So what we want to do is we want to look at, we want to start by looking at those scenarios. And what I'm going to do is I'm going to use the symbols, right? So for batteries, right, this is a battery. And then for us, so we'll see bulbs either like that as just like a squiggly line. I mean, really, that's the symbol for what we call a resistor. Or you'll see bulbs like this, a squiggly line with a circle around it to indicate a bulb. Either way, right? That's it. Either symbol is just a bulbs, and then wires are just lines. But they're not normally not curvy. They're typically straight. Not that that was much straighter than the first one. So in the circuits we built for the lab we started on Thursday last week, right? We had a battery and a wire that went around to a light bulb. And in last week's lab, I only gave you one wire, but here I'm just going to draw another wire that goes here to the back side of the battery, right? We talked about how this is a complete circuit, right? So that current is allowed to flow around the system through the bulb and back, right? We have current flowing in the system, and you need a complete loop, right? So that's just like a quick little reminder for what we did in last time's lab, and just to kind of think about how maybe some of those ideas are going to tie into what we're looking at today. So today we had three light bulbs, okay? And there are two different ways that you can hook up light bulbs in a circuit, right? The first one is called series. So you have a series arrangement, and the other one is called parallel, okay? You can have a parallel arrangement, okay? So with light bulbs in series, and by the way, right, this is how you get, for the first two tasks in today's lab, like here's the secret. Series light bulbs look like this. They're all in a line, and they're connected head to tail. And then this goes off, right? And maybe, most likely you're connected to the battery over here, okay? But that's series, right? And the important thing about series is that if I'm looking at the current, right, you see the current go out, it comes around, crosses through the first battery, crosses through the second battery, crosses through the third battery, and then comes back. And one of the things you have to ask yourself is, right, did that current, did it split ever? Did it break off into more parts than just one? And the answer here is no, right? It just followed a straight path and went through each of the light bulbs, and then it came back. Okay, so that's why we call that series, because it had to go through each of them in series. Okay, the other one, our parallel arrangement, is a little bit different. So in this one, so we come up. Let's say we're coming from the battery, right? Here's the battery. And then at this juncture, there's a branch, right? We split, and it goes one way, and it goes the other way. So here, I'm going to put one of the light bulbs here. And then this is going to loop back around. And then this comes up, and then I'm going to split again. Here's the next light bulb. And it's going to come up, and I'll come around, and I'll complete this. And so here's what that's what a parallel arrangement looks like, okay? And so you have the current leaves the battery. It hits this juncture, and it splits, right? Some of the current goes this way, and some of the current goes this way. And look, then there's another junction. The current splits again. So some of the current goes this way, and some of the current goes this way. Now the cool thing is that if we track this, right? So this current goes around, it goes through this light bulb and comes back down. But then when it gets here to this point, this current has traveled over here, and now the currents are going to come back together. So what split apart right here is now joining back together right here. And then this is going to come down. And then if you noticed, then now this is going to come back, like it's going to rejoin the current over here. And then it'll flow back to the battery. And so if I were to measure, if I were to look, I have the exact same amount of current here as I have here. Like, right, the exact same that left the battery is entering the battery on the other side, even though I may have some places in the circuit where it's splitting. Right, that's fine. But so looking at each of these, you have the series arrangement and you have the parallel arrangement. And so these arrangements of light bulbs are going to give you different results, right? If the current is splitting, that's going to give me one thing. If the current can't split and it has to go through everything, that's going to give me a different result. And so if you've experimented with these, this one is normally the one that students stumble on, right? It's pretty easy to kind of intuitively think, okay, well, I'm just going to go through the first and then the second and then the third light bulb, and I'll get them all to light up the same, okay? And when you did this, you should have noticed that in here, this is the dim case, okay? The light bulbs were all really pretty dim in the series arrangement, okay? Whereas if you were able to kind of figure out the parallel arrangement, and just to kind of visualize this, like what this would look like in the simulation, so here's your battery, and here's your light bulb. Let's see here. You have the light bulb, and the light bulb, here, I'll draw. Here's your other light bulb. Here's your other light bulb. And here, the light bulbs have a connection on the bottom and on the side. Connection on the bottom, connection on the side, connection on the bottom, connection on the side, right? That's how the light bulbs work. So you're going to have one wire. Notice I'm going to draw all these in green. So it's like I'm taking the bottom of each light bulb and I'm connecting each of them to the back side of the battery. Okay, and then I'm going to take this side and I'm going to connect each of these to this side of the battery. This circuit is the exact same as that diagram. And here, let me clean this up so that you can see why it's the same. So here's my battery again, coming up. Light bulb 1, whoops. Light bulb 2, light bulb 3, okay. So here's all the green wires. So it's like this wire comes off, green, green, green. Here's all the blue wires, right? These go back blue, 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 right? So, but each, right, this side of each light bulb is attached to this side of the battery. And this side of each light bulb is attached to this side of the battery. So that's why those are equivalent things, right? Those are parallel arrangements. And in this case, right, in the parallel case, you would have noticed that the light bulbs here were very bright. Okay, now, I have one huge caution with thinking of this in terms of like bright and dim. Okay, so notice here I only have things connected in series, and notice here I only have things connected in parallel. when you have this case, then yes, the series thing will be dim and the parallel thing will be bright. But if I mix these up, if I have something in series and something in parallel, by the way, that's how you get the third thing you were trying to accomplish in the lab. If you mix those up, then don't trust your dim and bright. Don't trust this, right? It's going to look a little bit different than that, and I'll talk you through how that works. Okay, but coming back and looking at this, when we're thinking about, right, what is series, what is parallel? Okay, series, the current doesn't ever branch; it stays all the same and flows through everything. Parallel, the current has to branch and it breaks into pieces, but those pieces always come back together. Okay, so series and parallel circuits. All right, let's talk about. So there's a trick that we use to deal with these circuits, and let me just show you. Okay, here's a battery. Let's send it across one light bulb and then bring it back. Okay, the most basic circuit that we can think about. Okay, there's a trick we can use to tell which of the bulbs in a circuit are going to be really bright and which of the bulbs in a circuit are going to be dim, like relatively speaking, right, to the other bulbs in the circuit. And we use colors to do it, okay? So what I like to do is I like to say, okay, I'm going to color this side of the battery red. I'm going to color this side of the battery blue. So I've got a blue and red side of the battery. And you've got a couple of rules, okay? Rule number one is that in a wire, you can't change colors. Change colors, okay? So for example, right, here's this wire. So this wire is going to be red, 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 and then I hit a bulb, and then I have to stop, right? If you hit an element, then that you have to stop, and now I have to change colors. Okay, but I've done the red side, and now I'm going to come back over here and draw the blue. So I draw blue, 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 and I hit the thing, and now I have to stop. Okay, now notice, I've colored all of my wires now, so I'm done. Okay, and so I can look at this light bulb here, and I can ask myself the question, okay, so what's going on with that light bulb? And now I'm going to draw what's called a voltage drop diagram, okay, where I start up here, here's the red, and underneath there's the blue. And so the way that all circuits work is it's like you can think of the energy that's stored in the battery as as the voltage that the battery has, right? It has a certain amount of energy, and that energy has to be consumed by the circuit as you move from one terminal of the battery to the other, okay? And so in this case, if I look, right, there's only one thing in this circuit. It's this light bulb. So what's connecting, so like this would be light bulb 1, right? So light bulb 1 has to consume, so let's say that this is I don't know, if this is a 2-volt battery, then this light bulb has to consume, right? This distance would be 2 volts. And this one light bulb has to eat up all 2 of those volts. Okay, and so the size or the amount of voltage that light bulb is eating, you can think of that as how bright it is, right? My light bulb, very bright bulb, because that one bulb has to consume all 2 volts. Okay. Let's change this. Let's change this scenario up just a little bit. So let's do a series where we have 2 light bulbs in series. So here's bulb 1 and here's bulb 2. So now if I'm going to use my coloring rule, right, you always start, this side's red, this side's blue, and now I'm going to color the red wire, color, 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 and stop. Because I hit a light bulb, color, 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 and stop. Okay, and then have I colored all my wire? Well, no, I haven't, right? There's still a little bit of wire in the middle. And so for the wire in the middle, you can pick whatever color you want. Normally, I like to go from like hot color, so like hot, and then yellow is not as hot, and then blues, the blue ones over here, and then maybe you could put green, right? Like a color progression where this is like high voltage to 0 volts. All the volts have been consumed, right? Um, anyways, so I don't know. Let's do yellow for this middle color. It doesn't matter. It's just a color. Um, okay, now I can go to I can look at this and say, okay, well, let's do a voltage drop diagram to match this. Okay, and again, this is just arbitrary. If I say that this is 2 volts, whatever, right? It's just saying that there's 2 volts here to consume, and I need to get from red to blue, but there's a yellow step in between somewhere. Okay, and now if I look at this, since these light bulbs are the same, right? We have in all of what we do, we're always going to assume that the light bulbs all have the same wattage. If they were different, then that would mess this up. But we're going to just kind of assume that all the light bulbs are the same. So, um, so these two, they're going to equally split and share that voltage drop. So I'd put something in the middle, and I would have light bulb 1, and there's light bulb 2. Here's 1 and 2. And they split that voltage up exactly the same. And so the cool thing is that if I were to compare this light bulb up to what's going on over here, notice that we're both dealing with a voltage drop of 2 volts, right? This light bulb 1 would be half as bright as this one because it's only getting half the voltage, right? But this bulb 1 and this bulb 2 right here, these guys, they're the exact same brightness, but they're only half as bright as the bulb from up here, okay? And you can kind of see what would happen if I had 3 bulbs in this scenario. So let's switch gears here a little bit, and let's look at what a parallel situation might look like. Okay, so delete those, and then let's say, okay, well, what would this look like if I had some parallel bulbs? So here's a battery going out here. So here's one. Well, let's just look at 2 bulbs in parallel. Okay, and again, we're just going to call that 2 volts just for fun. And now I'm going to say, okay, well, let's color. Okay, so this side of my battery is red. This side of my battery is blue. And okay, color, 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 stop. But now look, here's, in a wire I can't change colors. Notice this wire splits, but it's all still the same wire. So that's all red, right? All this wire is red. It's just wire. So that all has to be red. Now I come over here. So this is all blue, 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 blue. Okay, check that all out. All of that, it has to be blue. So I have bulb 1, I have bulb 2. And now when I draw this voltage drop diagram, okay, notice that if I look at this bulb 1, it's connected directly from red to blue. So I have to put the whole bulb 1 right here. And this bulb 2, well, it's also connected directly from from red to blue. There's nothing in between. There's nothing separating or splitting them up. Okay. And so in a situation like this, right, here's bulb 1, here's bulb 2, they both have equal brightnesses, and they're both as bright as they can be, right? It's like each of these light bulbs, so just as a comparison, right? So if I were to draw, like, look at this scenario. So here's my series, and so, okay, hold up, let me color. This would be red, this would be blue, and then this was yellow, and then, okay, here's the red and the blue, and then there's a yellow bit in between, and so, okay, here's bulb 1, and here's bulb 2. So looking at that, right, in the parallel situation up here, bulb 1 and bulb 2 are both as bright as they can be. They're each getting 2 volts worth of brightness. Here, bulb 1 and bulb 2, they're only half as bright as these top bulbs up here, okay? And if you took data like I asked you to do in the lab on on the speed of the electrons, you would have noticed that the electrons in this scenario were moving much faster than the electrons down here, okay? Because if I'm going to have 2 light bulbs at max capacity compared to 2 light bulbs at half capacity, this circuit up here is going to draw so much more current, right? I'm going to drain this 2-volt battery. I'm going to drain it way faster than I'm draining this battery. Okay. Anyways, but if we're comparing brightnesses, I think it's pretty clear to see that, hey, these 2 bulbs are very bright, these 2 bulbs are dimmer, but like looking at them in the same circuit, 1 and 2 are equal each other here, and 1 and 2 equal each other up here as well, okay? So I mean, I hope you're kind of seeing that like this coloring technique is really going to save us a lot of time, and it's going to do a lot of things for us, okay? So let's look at a circuit that's a little bit more complicated. So you see so on this page of the things, I'm not going to draw all of these for you because like part of like what Lou and I want you to do is to go through and to draw your own voltage drop diagrams and like experiment with this a little bit. But I do want to look at this scenario right here, which, by the way, this is the solution for part 3, or for the third task in part 1. So if I were to color this, so let's say, okay, look, this is all red, and it has to stop, and then come over here, okay. Now this is all blue, and it comes up here, and okay, still the same wire, so that's still all blue, and then I need a color for the stuff in between, but look, that's all still the same wire. Okay, so now I've got it colored, and now I want to say, okay, well, what does the voltage drop diagram look like for that? Okay, so here's the top and here's the bottom, and I've got to drop the voltage from the top, right? I have to get a voltage drop all the way to the bottom, and so how am I going to get there? Okay, well, I have a yellow step somewhere in between, right? Nothing is connected. And one of the things you can do is like you can look at each bulb. Look, this one has red on one side and yellow on the other. So it's nothing is a direct red to blue. This one has yellow on one side and blue on the other. This one has yellow on one side and blue on the other. And by the way, that's another way you can tell that these 2 resistors must be in parallel because they have the same colors on each end of the bulb. Okay? So anything that has the same color on each end of the bulb, that's going to be a parallel, like it's a parallel connection, right? These 2 bulbs right here, they're both yellow blues, so they're connected in parallel. This bulb right here is a yellow red, and there's nothing else that's a yellow red, so that's kind of like a little loner series bulb or whatever. Anyways, the next little bit that I need to show you here is we need to figure out where to put this yellow line. Does it go right in the middle? Does it go up here closer to the red? Does it go down here closer to the blue, right? Where does that yellow line go? And the way we determine this is we need to say, okay, who's the biggest consumer here? And the trick to this is, and this is really important, is that anything that's connected in parallel. So if I look at, if I kind of zoom in on this thing, right, this parallel connection, this is equivalent to, or it equals, a small resistance. Okay. So for whatever reason, and we'll talk a little bit more about why this is, but resistors that are connected in parallel, if I were to reduce this to just, if I were to reduce this to just one resistor, this one resistor has a small, or like one light bulb, this one, it has a smaller resistance than the thing that it came from. So for example, if this had a resistance of 4 and this had a resistance of 4, then the resistance of this thing which is kind of, and you can, so the resistance of this, which you can think of as the combination of these two, right? R is going to be less than 4. We could calculate exactly what it is, but that's a little bit beyond the scope of this class, and like getting into the mathematics of it is beyond what we want to do. But we want to kind of just learn the general principle or the trick that yes, that this thing is going to have a smaller resistance, and because the resistance is smaller, it consumes less voltage, which means I need to put the drop down here, right? I need to shift it down from the middle because I know that the drop that's happening here is going to be smaller than the drop that's happening here. Okay, because so if I erase this and you look, these are all 100. That little symbol is an ohm. 100 ohm light bulbs. So they're all the same light bulb. But when I connect these two in parallel like that, it's as if this one is in series with something that's smaller than 100. Okay, so the 100 light bulb is going to have a big voltage drop. So if I were to label these, right, if I called this 1 and this 2 and this 3, then resistor 1 is going to be there, and here's resistor 2, and here's resistor 3. Okay, the parallel nature of the two gives it a smaller drop, and this one all by itself gives it a bigger drop. Okay, and it's all based on this idea that when you allow the current to split and flow in two ways, it's less resistance. Kind of one of the ways that Lou likes to think about it is if you imagine that this is a pipe, and here the pipe can only go in one direction, but here the pipe splits. So it's like the barrel of the pipe was this big, but now since the current can go in two different ways, it's like I have much more pipe for the water or the current to flow in, and this larger pipe is less resistance, right? Less resistance. So it doesn't use up as much voltage. And we can kind of see that reflected in this part of the diagram up here. So if I was comparing the brightnesses of all of these bulbs, I would say, hey, this one's going to be the brightest bulb in the circuit because it has the largest drop. And these two are going to be dimmer than the first one because it doesn't have as large of a drop. And you can see that in the voltage drop diagram. Now I know, like, this is a lot, right? This is a lot to kind of take in and swallow in one go. And you're going to get to play around with, like, this one is a little bit more complicated. These ones, hopefully you can do just fine. This one's a little bit more complicated, and this one's really crazy. So for this one, I think you should be able to handle and draw the voltage drop diagram just fine. But this one down here, I just want you to do your best on this, and we will go through and look at all of these in a following video, and I'll kind of break everything down and explain it, and we'll do more examples of this stuff because it's going to end up being pretty important later. So go back through and watch this a couple of times, right? The principles in here are really important, right? We have series circuits, we have parallel combinations, right? Here's a parallel combination up here as well. This one's kind of cool because it's like you have these resistors in series, right? These two are in series with each other, these two are in series with each other, but then the set is in a parallel combination, and so you've got like two things going on, and that'll play out nicely in the diagram. But this video is already getting a little long. We're pushing 30 minutes, so let me wrap this up and just say that there's more to come, but you do have enough information right now to finish this lab, and we'll do a lot more practice with this on Thursday. So thank you so much. Have a great day, and please send Lou and I any questions that you might have. Thanks, everybody. Bye.